This video describes the fitting of scleral lenses using your Medmont E300 corneal topographer and the Scleral contact lens fitting module within your software. We know that the cornea begins to form a straight line or tangent shape at approximately a 10 millimeter chord. That straight line or tangent shape runs past the cornea, through the limbus, and onto the sclera, and the average angle at the 10 to 15 millimeter chord is approximately 38 degrees. When that angle is approximately 38 degrees, the depth of the eye shows a 2000 micron, what's called scleral sag factor. However, if the angle of the peripheral cornea and sclera that forms between that 10 to 15 millimeter chord is higher or lower than that average 38 degrees, then the scleral sag factor may not be accurate for 100% of eyes. To improve upon the error that may exist by using the scleral sag factor in some eyes, the Medmont topographer is able to calculate the corneal sagittal depth to a 10 millimeter chord, but also to determine the angle that forms at that 10 millimeter chord 360 degrees around. Therefore, when your Medmont can measure the corneal sagittal depth, in this case 1970 microns, and it can measure the angles that form 360 degrees around the eye surface, therefore a rigid contact lens can be predicted to fit well past the cornea. And this is the unique feature of the Medmont software. It allows a scleral lens with diameters that fall well past the measured placido reflection and can be predicted for their bearing and lift 360 degrees around. When coupled with the new composite feature available from your Medmont topographer, you're able to map 100% of the eye's surface by changing the fixation of the patient and taking captures on each area of the cornea. When stitched together to create what's called the Medmont composite eye, we're able to understand 100% of the corneal surface and therefore predict that angle that forms at the 10 millimeter chord more accurately. This allows the Medmont software to generate a theoretical scleral lens. We drop that lens on eye and we can observe the tear film that exists 360 degrees around using the white axis line. By taking this little handle and rotating it around, you're able to observe the fluid layer underneath this lens. In this case, before we put on this 16.5 diameter lens, we see that very close to the limbus, at approximately 16 millimeters out and through the peripheral cornea, the lens shows less than 80 microns of fluid. We know that scleral lenses will sink by approximately 100 to 150 microns into the boggy conjunctiva, so that could eliminate that clearance that we presently have through the peripheral cornea and limbal area. In this case, this patient had a very high angle. Notice the angles of nasal and temporal sides were approximately 43 degrees on the nasal side, 42 degrees on the temporal side, for an average of approximately 42.6. The normal angle is 38 degrees. Therefore, this patient has a much higher scleral sag factor of 2,300 microns. When the Medmont software predicts the initial lens, notice that it's telling you that the eye surface is very high out in the peripheral cornea and limbus, and therefore your scleral lens may have inadequate depth. By adjusting the fit of the lens in the Medmont software, we're able to increase the limbal clearance zone vaulting and allow for more depth before we put that lens on eye. So it's a very accurate way of determining both the initial sagittal depth required, the apical clearance of your lens, as well as what should the limbal clearance or limbal vaulting of the lens be. If we do this within the Medmont software, we can take our normal fixation map, then we have our patient look nasal on this right eye, have the patient look temporal, have the patient look superior, have the patient look inferior. We take all of the maps together, go up to analysis and composite eye, and build a larger view of this eye shape. Here is your composite eye, and notice how the colorized analysis goes well past the cornea, 360 degrees, to reach the limbus. There's no areas without any calculation of eye shape. So to determine the proper scleral lens, we may have the optimal map now to begin. And the Medmont has this unique feature of being able to capture multiple images and stitch them together to create this larger view called the composite eye. Let's select our scleral lens from the fitting software and punch in the RX for the patient. Then the Medmont software will create a theoretical fluorescein pattern of our scleral lens. The first thing to note is that the fluid layer in the center is approximately 382 microns. It's past the y-axis of our tear profile graph. So let's change our standard fluorescein to the scleral lens fluorescein pattern and look for the axis of most bearing. As we drag this axis line around, find the axis where you have two opposing points of bearing, and this would be one of those areas of bearing. The next thing we can look at is the amount of apical clearance. In this case, the eye shows, when we click our cursor in the center, a 382 micron apical clearance of our scleral lens. When the lens is dropped on eye, we want approximately 300 to 400 microns of apical clearance, because we know scleral lenses will sink by approximately 100 to 150 microns. Therefore, with our initial 382 microns of apical clearance, we have the desired initial apical clearance. However, we know that lenses will settle by approximately 100 microns. So let's model the settling of our scleral lens by this 100 micron margin and determine if the lens will drop into peripheral corneal or limbal bearing. And you can see after the lens sinks in to the conge, you have an appropriate amount of fluid vaulting through the limbus at approximately 6 millimeters out on each side. We have approximately 160 microns post-settling clearance. If we felt we wanted to change the clearance to create additional vaulting, we can modify the limbal clearance zone of the lens here and apply. Notice how that increases that limbal clearance zone vaulting. If we felt we needed to decrease the vaulting through the limbal clearance zone, we can model that in the Medmont contact lens software prior to putting the lens on eye. Now we have only approximately 100 microns of fluid in the peripheral cornea and limbus. In the center, we've dropped that lens down to 166 microns of apical clearance. So we can fit the scleral lenses in the theoretical environment here before we fit them in the actual environment. And this will help to create more efficient scleral lens fittings.